Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss about heads and efficiencies of a centrifugal pump. What are the different type of heads and efficiencies which is involved in the centrifugal pump? We'll discuss one by one. So first one in the head, we'll discuss about the suction head. So first one, we'll discuss about the suction head. So suction head, to understand the suction head, I have taken the diagram of centrifugal pump. The same diagram we have discussed regarding the working principle of centrifugal pump. If you see this centrifugal pump, this is the center line of the centrifugal pump. Okay. So from the center line of the centrifugal pump to the surface of the water level, this distance is called suction head. And the suction head is actually denoted by HS. Okay, this is denoted by HS. So you can see this is the suction pipe which is used here to suck the water or to lift the water from the sump level or from the water level, you can say. So this is suction head, or we can say the vertical distance from the sump level or from the water surface to the center line of the pump, that is suction head. Next one is the delivery head. This is the second one. This is delivery head. This is also simple. And this is delivery head is denoted by HD. Okay. Now you can see in this pump, from one level the water need to be sucked, or from the water need to be lifted, and another level or another distance, like up to which the water need to be delivered. Okay, so this lifting and delivered work will be done by the pump. So the distance from the center line to the distance or to up to which the water need to be delivered, that is called delivery head. Or you can say that vertical distance between the center line of the pump and the water surface of the tank or the place where the water need to be delivered. That distance is called delivery head, and that is denoted by HD. The next one, that is called static head. The next one is static head. The static head actually it is to denote by capital HS. So capital HS is nothing but, if you see, if I'll take the distance like total height from the surface level of water to the location up to what the water need to be delivered, that distance. So we can say the static head is the sum of suction head. This is nothing but sum of suction head plus the delivery head is known as static head. So we can write in this way. Okay. The next one is manometric head. The next one is manometric head. This is a little bit important than the other heads what we have discussed. Like everything is important, but this concept is to come in the exam to identify or to solve the problems actually. So manometric head is also similar kind of head. Okay, but it's slightly different. That here directly we are showing that from the center point to here, that is suction head. If I'll write this one, so you can write like a center line of pump to, like you can say the sump level or water surface. Water surface at sump, this distance. Similarly here if you write the same thing again, like center line of pump to the like you can say the upper tank, upper limit of the tank or the upper level of the tank, or the location you can say at what the water need to be delivered. Okay, or the fluid need to be delivered. Location of delivery, it may be anything. Okay, this is the delivery head distance, and this is nothing but sum of, you can say, This is sum of suction head plus HD. That's same thing I have written. Now the manometric head, actually, this is defined as the head against which a centrifugal pump needs to work. Okay, this is the head against the centrifugal pump needs to work. What is the meaning of this? Actually, the manometric head is denoted by HM. Let me write this HM. So HM will be can be written in different types also. I'll tell a few types are there. First one, let me write. HM can be written the head imparted. First thing, the head imparted by the impeller, impeller to the water, okay. This is HM. This is not the full definition or full this one formula for this. Head imparted by the impeller where this is the impeller. So these are the parts which is involved in the centrifugal pump. Already we discussed previously, no need to repeat again. So this is impeller, casings and eye of the pump. This is shaft, okay. This suction pipe, delivery pipe and delivery valve, suction valve will be there. So here the head imparted by the impeller. So impeller is already there, okay, to the water. So water was first initially it is to be lifted, then it is to strike at that eye of this pump or at this point impeller, then it is to move like this through the vents. Anyway, so manometric head is nothing but the head imparted by the impeller to the water minus the loss of head in the pump. The loss of head in pump. So what are the losses of head will be in the pump? See, when there is a liquid is flowing or fluid is flowing, so obviously some kind of losses will be there. So losses of energy already we have studied previously in the fluid mechanics, like major losses will be there and minor losses will be there. So when liquid is or fluid is flowing, there may be minor loss or maybe major loss. Major loss due to the friction and minor loss is to happen due to the at the suction inlet of the pipe, outlet of the pipe, then valves, joints, so many things are there. So this loss of head in the pump need to be considered. So here head imparted by the impeller to the water is nothing but what is the work that happened at the impeller to the water. So this one we can write HM. So one more time let me tell you what is this exactly. Suppose, see here, if you see the total height is given here, up to this it is given, correct, okay. The total height is given this much, you can say this is H, suppose, okay. This is total head need to be given, like total distance need to be supplied from this level to that level, but due to the friction, this much need to be supplied or this much need to be delivered. So if you see, suppose this is our H, I'll write just normal H, I'll write here, okay. The water need to be supplied from here, like it need to be lifted from here and it will be supplied to up to this distance, but due to this losses, this much distance was not able to supply or not able to deliver. So up to this distance only it can be delivered. So this distance is nothing but HM, and this distance is coming under losses, like coming under the losses in the sense due to the losses this much distance was not able to cover. So here we can write the head imparted by the impeller to the water is nothing but the work done. So we have seen previously in a previous lecture what is the work done by the impeller to the water, that is nothing but VW2 U2 by G. And what is the losses of head? So this is, we can write the loss of head in, see the loss of head in the pump is nothing but in the pump, what if you see what are the things are there, impeller is there and here casing is there, okay. So the loss of head in impeller, we can write the loss of head in impeller and casing. If any losses will be there, that means in between these two components, impeller and casing, that losses need to be considered. So if losses will be there, then this will be the equation. If suppose the loss of pump, the loss of head in the pump will be 0, then what we can write? then we can write HM equal to VW2 U2 by G. This is our if loss of pump is 0. Here we can write if loss of pump is negligible or 0, suppose, then we need to consider this formula. So this will be not considered. So this is one category. The second one, okay, this is first one. Second one is nothing but HM, you can write the total head. This is at the inlet condition, suppose if you consider. Now we can write the total head at outlet of the pump. Okay, outlet of the pump in the sense at this point, like total delivery, we can say. So the total head, I'll write total head in this way, total head at outlet of pump, outlet of pump minus the total head at inlet of the pump, inlet of pump. So what are the head here? Total head in the sense, we have already discussed these things during the Bernoulli's equation, if you remember. So total head is nothing but we need to consider here the Bernoulli's equation, like pressure energy or pressure head, then velocity head, potential head. So at the outlet condition, we need to consider like PO by rho g. This is the formula actually, PO by rho g. Then we can write this is V square by 2g actually. So I have written VO square by 2g plus potential head will be there. So that is the distance from this label to up to, like you can see at what point that pump is situated. So the distance, so that is Z naught, support at the outlet condition. Similarly, the total head at inlet condition of the pump is nothing but here we can write at inlet condition, correct? So we can write Pi by rho g, and this is you can write plus, you can give it bracket, let's keep it in the bracket, and this will be also in the bracket Pi by rho g, and this is Vi square by 2g, and this is Zi. Okay, so this is the manometric head, the total head at the outlet of the pump or minus total head at the inlet of the pump. So these values actually already I told previously. Again, if you want, I'll tell you, this is P by P naught by rho g. This is nothing but pressure head at the outlet, pressure head at outlet, O for outlet, at outlet condition. And this one also we can write HD. This is nothing but HD, what I've written. Similarly, this is V naught square by 2g. This is already told you that velocity head. Similarly, at the outlet conditions or at the delivery pipe also you can say. So that one we can write. This is in terms of Vd square by 2g also we can write. And Z naught is nothing but the vertical height of the outlet of the pump from the datum line. So we need to consider a datum line, like from which line the distance need to be considered. Either you can take a reference line or this line, some reference line we need to consider to measure that. So that is Z naught. That's it. Actually, you can say that height, vertical height at the outlet conditions. So similarly, that inlet condition will be like this is Pi by rho g and Vi square by 2g. Similar corresponding values for pressure head and velocity head and datum head. Okay, height from the datum line. So this one, if you can write, okay, or datum head also you can say. Now, these things also we can write in terms of suction part also, because this one is a delivery part and this is will be this part will be the suction part. So this one we can write as I have written here HD. So this one I can write HS, correct? This one I can write, this is BS square by 2G, and this one also as I can write, this is ZS. Okay. Now one condition I will tell you, if suppose our diameter of the suction and delivery pipe both are same. So diameter of suction pipe and delivery pipe will be both are same, means this part will be same, like V naught square by 2g, and here vi square by 2g both will be same, and this datum line z o and zi will be same in the sense, then we can get hm equal to we'll get this is p naught by rho g minus pi by rho g, and this one we can write p naught minus pi by rho g, or else we can write this is hd minus hs. If what I mean to say, if our this velocity head both are equal, okay, then for this condition we can get this, okay. And the last one more formula is there for this hm, manometric head. What is the formula for this? Like hs, suction head, plus delivery head, okay, plus hfs. So hfs is actually nothing but what is the frictional head loss. As I told you, frictional loss, when it will come, when major loss will be there. Major loss means when the flow is flowing in the pipe, okay. So this is hfs, similar as the suction pipe. Similarly, flow will be there in the delivery pipe also. See, when the water is flowing, it is flowing through the suction pipe as well as in the delivery pipe. So hm you can write hs plus hd plus hfs, and this is hfd. So this is frictional head loss in the delivery pipe, plus what is the velocity of water in the delivery pipe. This is v square by 2g, okay. At the outlet condition, what are the losses are there. So this will be also one equation for the manometric head. So these three equations we can remember. It can be used like when some kind of problem will be given to solve this, we can use this one. Yeah, this is one, this is one, this is one. So these are all the heads of a centrifugal pump. Now we'll discuss about the efficiencies. So before going to the efficiencies, once have a look on this pump, because from here only we are going to identify what are the pump efficiencies are involved in the centrifugal pump. So first one, if you see, we'll discuss about the like what are the efficiencies are there. Basically, we have already seen previously like manometric efficiency, then overall efficiency, then mechanical efficiency, then volumetric efficiency, and okay, like that some efficiencies are available. So here if you see, here shaft is there. So shaft need to be started. So shaft will be started with the help of motor. So here if you see, the shaft will be connected to the motor. Once you switch on the motor here, then the shaft will be started running. The shaft is mounted the shaft is connected to the impeller, okay. So that means the pump is going to start. So the power will be shifted from the shaft to pump, okay. Then from this pump to the power will be shifted to the impeller, then from the impeller to water. So this is the process of efficiency, or you can say the power transmission, we can say, in the pump. So for the efficiency, let me write, yeah, for the efficiency, first one I'll write manometric efficiency. So manometric efficiency I'll write directly like this, short form. So manometric efficiency is nothing but this is the ratio of manometric head to the head imparted by the impeller to the water. Or I can say, this is very simple, we can say that is the manometric head, it is the ratio of, we can say, the manometric head to the head imparted by the impeller to water, okay. That is nothing but power at the power of impeller. So this is shortly we can write power of impeller, or the head imparted by the impeller to water. So I'll just write, this is short, power of impeller, okay. So this one what we can write as the formula. So manometric efficiency, we can write, this is manometric head. What is the manometric head? We have seen that is hm, as simple as that. And power of impeller is nothing but the head imparted by impeller to water is nothing but what is the work done or what is the power at the impeller. So that one we know the formula, that is nothing but VW2 U2 by G, and here we can write this is HM. This G denominator part, let's take it to the numerator. We can write like this. This is VW2 U2. Okay, this is our manometric head. Okay, this is our manometric head, manometric efficiency. And this one also, some books, it will be given in the different ways to find out, like actual power delivered by the pump and with respect to the power imparted by the impeller. Okay, see, manometric head is nothing but what is the power is actually delivered by the pump. So in that way also we can calculate one more I'll show you here. Here actually how it will be given the actual power delivered by pump, actual power delivered by pump, and this is as usual like power imparted by the impeller. So this is power imparted by impeller. So what are the formula we can write? See, here I'll slightly different. I'll write the different formula for this. Means both are same, but here this is nothing but water power. Water power here we can write. This one I will write. This is water power with respect to impeller power, IP. Okay, keep in mind IP you can write for impeller power. So water power is nothing but we can write this is rho G Q. Manometric I told you. So here I'll write the HM part. Okay, this is water power with respect to the manometric head. Here impeller, power imparted by the impeller, nothing but the work done. So this one also we can write along with this impeller power. Same thing like rho G Q along with this formula VW2 U2 by G. So this will be cancelled. The same thing will get it here. Okay, some books will be given in that way, some books will be given in this method also. So both are correct, you can see. This is about the manometric efficiency. And second one, we'll discuss about the mechanical efficiency. So mechanical efficiency is the important one because your power generation, you can say. So mechanical efficiency, it indicated by eta M. Okay, and here the formula is the definition is it is the ratio of power at the impeller, power at the impeller to the shaft power, or power at the shaft. We can write power at the shaft, as simple as that. We can also write in this way. This is impeller power. Let me write impeller power by shaft power. Okay, so what is impeller power? Already we have seen previously impeller power is there. So this one we can write. Okay, power at the impeller in this one we can write mechanical efficiency equal to, if you want to write, this is okay, power at impeller. Here also we can write this is W by G. I am writing in terms of work done also. Okay, so W by G, G in the sense here I'll write this is VW2 U2 by G, and this is 1000 in terms of kilowatt, and divided by this will be shaft power. This will be shaft power, and finally we can write this mechanical efficiency. We can write this is W VW2 U2 by this is G into 1000. Shaft power into 1000 into G. This is our mechanical efficiency. Okay, the next one is I can write this is hydraulic efficiency. One more is there, hydraulic efficiency also there. So hydraulic efficiency is very simple. It is the ratio of, we can write it the ratio of hydraulic power to the you can say the runner power. Here runner is not there, impeller power, or we can say it is the ratio of hydraulic power to the mechanical power supplied. So let me write we can write this is the useful hydraulic power, at outlet or at output, we can say at outlet or output, and what is the power was supplied to the at the inlet. So that one we can write in terms of mechanical. So mechanical power at input or at inlet, that is hydraulic efficiency. Next one is volumetric efficiency. One more is there, and this is, we know already, previously also we have discussed. Volumetric efficiency is nothing but Q actual by Q theoretical. Okay, that means it is the, we can say it is the ratio of actual flow rate or actual discharge with respect to the theoretical discharge. This is volumetric efficiency. And the last one is nothing but overall efficiency, eta O, we can write. So it is the ratio of, we can say, actually I'll write in this way. It is the ratio of like power output at the pump, power output of the pump and power input to the pump. Anyway, we know that efficiency is nothing but output by input. So similarly, what we can write, like power output of the pump, by power input of the pump. Okay, this one we can write in this way, or I'll tell you one thing, one more is there. Also, this overall efficiency is to called, it can be written like water power by soft power, and this one I can write again water power by impeller power into, again impeller power, just multiply it, here divided, here multiplied by soft power. Now you see water power by impeller power, what is that? We have seen already. I can write this is water power by impeller power is nothing but manometric efficiency, and impeller power by soft power, if you see, that is mechanical efficiency. So we can write in this way also, the overall efficiency is nothing but manometric efficiency into mechanical efficiency. I hope you understand this efficiency of pump and the head of the centrifugal pump. If you are having any kind of doubt and query regarding this, you can give the comment on the comment box. Thank you.